In this video, we will discuss the rotation of a particle or body around an axis. In many ways, it is similar to linear motion, but the variables and components we measure are different. Let's look at a rotation. So we have a body rotating in this direction, and if we call this theta 1 and theta 2, this is the radius, this is time 2 and time 1 as it rotates, and this is a segment ds. So we know that in a case like this, theta is equal to s over r, where theta is measured in radians. And we'll use radians for most of this topic. So one complete revolution around the circle is 360 degrees, and that's equal to 2 pi radians. So if we look at the change in the angle, which is equal to theta 2 minus theta 1, that becomes our angular displacement. And that's just the movement of the particle around the circle from theta 1 to theta 2. And by definition, if the displacement is counterclockwise, that's considered a positive displacement. If it's clockwise, then that's a negative displacement. Now, we have a term called angular velocity, which is little omega, and that's equal to the change in our angle over the change in time, or delta theta over delta t. And the units for that is radians per second. So this would be your average angular velocity. That's the rate it's moving around the circle. If we want our instantaneous omega, that's equal to d theta dt. And again, if omega is moving counterclockwise, then the velocity is positive. If it's moving clockwise, then the angular velocity is negative. We also have an angular acceleration, or alpha. And the average angular acceleration is equal to the change in our angular velocity with time, or delta omega over delta t. And the instantaneous acceleration is given by d omega dt. And the units for acceleration here are radians per second squared. Now, we represent the angular velocity omega as a vector along the axis of rotation. So if we have a rotation in this direction through an axis that goes through the middle, omega is actually along that axis of rotation. And we determine which direction it is through the right-hand rule. So from this diagram, you can see the right-hand rule determines the direction of the axis of rotation. If you curl your fingers in the direction of the circular motion, your thumb points to the direction of the angular velocity. And if the direction points up, that's positive. And if the direction points down, that's negative. So this would be a positive, and that would be a negative. And note that the angular velocity vector defines the axis of rotation, not the direction of motion. And we also have a vector for acceleration, and that is also up or down. And if the acceleration and the angular velocity are in the same direction, that means that the rotation is speeding up. If the angular velocity and acceleration are in opposite directions, that means the rotation is slowing down. Just as with linear motion with constant acceleration, we have a special case of motion with constant angular acceleration. We get kinematic equations similar to linear kinematics, and you can see these here. And in each of these rotational kinematic equations, one component is not used. And as in linear mechanics, we can use that fact to help solve problems. Now, the linear measurements during rotation are related to the angular measurements mainly through r, the radius of rotation about the axis. So let's look at these relationships. So let's say we have a rotation, and we have our radius r, we have our velocity, tangential, going that way. We have our angle angle theta, and our segment S. And again, we're using radians for most of these units. Well, S equals theta times r, so ds dt is equal to d theta dt times r, or ds dt is our instantaneous velocity. That's equal to angular velocity times r. So this is one relationship between linear and angular components. Now, note that all points in a rotating body have the same angular speed, omega. But the linear speed, v, will vary as you increase r. That's why it's easier to use angular velocity and acceleration when doing rotational problems. Now, we also had a period, which is the time it takes to do one rotation, and that is equal to 2 pi r over velocity, which then becomes 2 pi over omega. And let's call this equation 1. So from equation 1, if we take the derivative of it, dv dt, that is equal to d omega dt times r. Or we get acceleration is equal to angular acceleration times r. But in this case, this acceleration is tangential. So let's draw another circle. We have acceleration radial and acceleration tangential. And the radial component of the angular acceleration is equal to the linear acceleration. That is, the acceleration radial, which is normal equal to v squared over r, and again using equation 1 above, that becomes omega squared times r. So now we're relating the linear acceleration to angular acceleration and velocity. When we talk about kinetic energy during rotation, the first thing we have to talk about is rotational inertia. And rotational inertia is I, and that's equal to the sum of the masses times the radiuses squared, and this is in kilogram meter squared. So this equation is good for a few particles, 1, 2, or 3 maybe. But if you have many particles, then we will use the equation I is equal to integral of r squared dm, which is equal to the integral of r squared times density times d volume, which becomes, since density is a constant, the integral density times the integral of r squared times derivative of volume. And if you recall in the previous video, we did use the density a lot. Now, then our rotational kinetic energy can be written as 1/2 rotational inertia times omega squared. This brings us to something called the parallel axis theorem. And the parallel axis theorem is a shortcut to finding the rotational inertia if the axis of rotation is not through a body's center of mass. So for example, if you have a mass and this is going through its center of mass, we'll call that center of mass, but the rotation axis is over here. So this is the rotational axis. It can be hard to find what its rotational inertia is through this axis. So if h is the distance, the perpendicular distance between the given axis of rotation and an axis through the center of mass, which is this one, then you can find inertia I by looking at its inertia through the center of mass, which is very often given by these types of diagrams, plus its mass times the distance between the two axes. And very often you would use A and B and get that h equals the square root of a squared plus b squared. And we'll see this on some of the problems we do. But this is what the parallel axis theorem does. Now let's talk about torque, or tau. In linear motion, we had a force, and that caused an acceleration. Well, for angular motion, rotational motion, the force we use is torque. And let's see what we mean by torque. So if you have an axis of rotation, and you have a force acting over a radius r, rotating about that axis. And if we take the angle between the radius and the force as phi, we would say torque is equal to r times the force times the sine of phi. And it's force times sine of phi because we want to know what the force is in the tangential direction compared to radius. Now, if you bring this force back to where it's 90 degrees, and we call this the radius perpendicular to the main force, then you can also determine torque by using that radius perpendicular to the force times the total force. So it's perpendicular radius times the total force. Or we can find the force tangential, and that's equal to the total radius times the force tangential, which is what F sine theta is. So there's two ways to calculate torque, and the units of torque are Newton meter. And if the force causes an angular acceleration counterclockwise, then the force is positive. If the force causes an angular acceleration clockwise, then the force is considered negative. And just like F equals ma, torque is equal to inertia times angular acceleration. Let's talk about rotational kinetic energy and work. We know that a change in kinetic energy, which is equal to final kinetic energy minus initial kinetic energy, is equal to work done. And that's the work energy theorem. Well, the same holds true for rotation. In this case, the kinetic energy, the final kinetic energy, is 1/2 inertia times angular acceleration final squared minus 1/2 inertia times angular acceleration initial squared. And that's the work done during the rotation. And similar to linear motion, where work is equal to the integral of f dx, for rotational motion we have work is equal to the integral of torque times d theta from theta 1 to theta 2. And if torque is constant, that can come out of the integral, and we get torque times the integral from theta 1 to theta 2 d theta, or work is equal to torque times theta 2 minus theta 1. Well, when we go to look at power, we know that power is equal to the time the work was done. And if we take the change in theta versus dt, we get that is equal to power is equal to torque times angular velocity. Time for some problems. A potter's wheel of radius 0.5 meters is spinning with an angular acceleration of 3 rads per second squared. A point A lies on the rim of the wheel. How far does point A move in 2 seconds? What is the angular speed, omega, at 2 seconds? What is the tangential or linear speed, v, of point A? What is the tangential acceleration? What is the centripetal acceleration after 2 seconds? So let's draw this. We have a potter's wheel, and we have a point A on the wheel. The radius is 0.5 meters, and it's moving with an angular acceleration of 3 rads per second squared. And we know its radius is 0.5 meters. The first part asks, how far does point A move in 2 seconds? Well, if we go over our rotational kinematic equations, we find the best equation to use for part A would be theta minus theta 0 equals W0t plus 1/2 alpha t squared. That's 0 and that's 0, because point A is at rest at the beginning, and we get theta is equal to 1/2 times 3 times 2 squared, or theta is equal to 6 radians. That's how far point A moves. The next part, part B, asks what is the angular speed, omega, at 2 seconds. So again, given what we know, the best equation to use is omega is equal to omega 0 plus alpha t. And we're looking for omega, that's equal to 0 plus 3 times 2, which is equal to 6 radians per second. That's the angular speed of point A at 2 seconds. Next part asks, what is the tangential or linear speed of point A on the rim? So we know that linear speed is equal to omega times the radius. And we know that omega is 6 and the radius is 0.5 meters. So this becomes 3 meters per second. Part D asks, what is a tangential acceleration? So A tangential is equal to alpha times r, which is equal to 3 times 0.5. So that is 1.5 meters per second squared. And E, what is the centrifugal acceleration at A at 2 seconds? Well, we know centripetal acceleration is v squared over r, which is also equal to omega squared r. So that would be equal to 6 squared times 0.5. So centripetal acceleration comes to 18 meters per second squared. And this isn't 0 because the direction of the velocity is constantly changing. So even though the velocity is constant, its direction is changing, which gives it a centripetal acceleration. Our next problem states, a car drives in a circle with an angular speed, omega, of 8 revolutions per second and a uniform acceleration, alpha, of 16 revolutions per second squared. It goes around 6 times. How long does it take to complete the 6 revolutions? And what is the final angular speed after 6 revolutions? So, one thing to note If you're working only with angular variables, you can leave everything in revolutions per second. However, if you're using tangential variables, such as velocity tangential or acceleration tangential, then you need to convert everything into radians first. So, getting back to the problem, how long does it take to complete 6 revolutions? So, looking at our rotational kinematic equations, the best one to use is theta minus theta 0 equals W0t plus 1/2 alpha t squared. And in this case, we know that the displacement is 6 revolutions, and again we're using revolutions, not radians. That is equal to, well, W0 is 8 revolutions per second times t plus 1/2, and the acceleration is 16 revolutions per second squared times t squared. So if we bring the 6 over to the right side, we get 8t squared plus 8t minus 6 equals 0. And guess what? That's the quadratic equation. And we know how to solve those. So if we put it in the quadratic equation form, t is equal to minus 8 plus or minus the square root of 8 squared minus 4ac over 2 times 8, which equals minus 8 plus or minus the square root of 256 over 16, which equals minus 8 plus or minus 16 over 16, which gives us 2 answers. If you add and subtract the 16, you get either t can equal 0.5 or minus 1.5 seconds. Well, since we can't have a negative time, the time is equal to 0.5 seconds. That's our answer. In part B, we want to know what is the final angular speed after 6 revolutions. Well, the equation to use, W is equal to W0 plus alpha t. And we know W0 was 8 plus 16 times 0.5. So that's equal to 8 plus 8, or our final angular speed is equal to 16, and in this case it's revolutions per second. Here's our next problem. A 40 kilogram box sits on the end of a 60 kilogram board that is 20 meters long. There is a fulcrum 4 meters from the left end of the board. What is the torque exerted by the box? What is the torque exerted by the board? So we can diagram this one. Here's our board, and the board is 20 meters long, and there's a fulcrum 4 meters from the end, and there's a box that weighs 40 kilograms, and the board weighs 60 kilograms. So we want to know what is the torque exerted by the box. So in this case we have the box, a fulcrum, and we have the distance R1 from the fulcrum to the box. So torque is equal to, and this is torque of the box, is equal to R1, force 1, times sine theta. And in this case, theta is 90 degrees. So that's equal to, now R1 is 20 minus 4 meters, which is 16 meters, times the force, which is the weight, so that's 40 kilograms times 9.81, times the sine of 90 degrees, which is 1. So this becomes 6278.4 Newton meters. That's the torque exerted by the box on the board. Now, what about the torque exerted by the box? By the board. So again, you have your board of fulcrum at 4 meters. The center of the board is at 10 from the end. So the distance from the fulcrum to the center of mass of the board is 6 meters. And once again, the torque of the board is equal to, and this is R2, is equal to R2 F2, and we'll call that F2, times sine theta. So that's equal to 6. And again, the force of the board is its mass times G times sine 90 again, which is 1, and that comes out to be 3531.6 Newton meters. And those are your answers. A string is wrapped around a cylinder of radius r and mass m. The string is pulled upwards as the cylinder unwinds so that the center of mass of the cylinder does not fall. What is the tension in the string? What is the work done when an angular velocity omega is reached? What is the length of string that unwinds during the time it takes to reach angular velocity omega? So let's diagram this. We have our cylinder with string wrapped around it, and this is the string, and this is going to unwind in this direction. We have the weight of the cylinder pulling against the string, and we have the radius r of the cylinder. So as we're pulling up on the string with a tension, the weight is pulling down, and that's causing the string to unwind. So for A, we first start with our equation of motion. And we know from Newton's law that ma is equal to mg minus t. That describes the motion of the cylinder. Well, we also know that torque is equal to the force over the radius, which is the tension over the radius of the cylinder. And that's also equal to a moment of inertia times angular acceleration. And for a cylinder, that becomes I, which is 1/2 mr squared for a cylinder, times at over r. This is the angular acceleration, and this is the moment of inertia. So if we use these two equations, we can solve, well, let's just write them out. TR is equal to 1/2 mr a tangential. So we'll call this equation 1, and we'll call this, we can break this down further. T is equal to 1/2 And we'll call this equation 2. So now that's the tension in the string. Now if we put 2 into 1 above and solve for A, we get MA is equal to mg minus T, or MA is equal to mg minus 1/2 MA tangential. These cancel out, and what we end up with is A tangential is equal to 2/3 G. And if we put that back into equation 2, we get T is equal to 1/2 M times 2/3 G. Okay, from there, or T ends up being 1/3 mg. That's the tension in the string as you're pulling it up. Now we want to know what is the work done as angular velocity omega is reached. So we know that work is equal to a change in kinetic energy, which is equal to kinetic energy final minus kinetic energy initial. But in this case, we're starting from rest, so that's 0. So work is equal to kinetic energy final, and we know in rotational motion, kinetic energy is equal to 1/2 I times omega squared, which is equal to 1/2, and I for a cylinder is 1/2 mr squared times omega squared. So work becomes 1/4 mr squared omega squared. That's the work done when you reach omega squared. For the last part, we want to know what length of string unwinds during the time it takes to reach angular velocity omega. So we know that work is equal to the integral of tau d theta in rotational motion, which is also equal to tau theta, which is also equal to F times R. And in this case, the force is mg and the R is a radius, and that's equal to mg times R times theta. So if we put in the equation we found for work from part B, where we found work is equal to 1/4 mr squared omega squared, we now can equate that to mg r theta, and the m's cancel out, one of the r's cancel out, and we end up with 1/4 r omega squared is equal to g theta, or theta is equal to 1/4 r omega squared over g. Now, knowing theta, we can find the length of string, because a segment in a circle is equal to theta times the radius. So if we substitute theta in here, the length of string is equal to 1/4 r squared w squared over g, substituting this in for theta. And that's the length of string that we'll have unraveled when we reached the angular velocity omega squared. Let's do one more problem. A uniform rod is attached to the outside of two hollow spheres. The rod is 10 meters long and has a mass of 6 kilograms. One sphere is 10 kilograms and has a radius of 2 meters. The other sphere is 4 kilograms and has a radius of 1 meter. An axis of rotation goes through the center of the rod. What is the moment of inertia about this axis? Well, we're going to use the parallel axis theorem to solve this problem. Without that, it would be very hard to solve it. So let's diagram it first. So we have a rod, and this rod is 10 meters long and weighs 6 kilograms. It has a mass on one end and a smaller mass on the other end. And this mass is 10 kilograms. And it has a radius, we'll call it R1, of 2 meters. And this mass is 4 kilograms and has a radius R2 of 1 meter. There is an axis through the middle of the rod that the system revolves around. And we want to know what the moment of inertia is about this axis of rotation. So what we're going to do is find out what the moment of inertia is for each of the spheres and the rod, then add them together using the parallel axis theorem. So the moment of inertia for the rod is equal to 1/12 times m times its length squared, which is equal to 1/12 times its mass, which is 6, times 10 squared. So the moment of inertia of the rod comes out to be 50 kilogram meter squared. Now, what would be the moment of inertia for a sphere? Normally, that would be I of a sphere is equal to 2/3 mr squared. But this is for a sphere where the axis of rotation goes through the middle of the sphere. And we actually have the sphere revolving around a different axis of rotation. So this is why we have to use the parallel axis theorem. So let's look at that. That says that the moment of inertia of the sphere would be equal to the moment of inertia through the center of mass of the sphere, which is this, plus mass times h squared, where h is the distance the sphere center of mass is away from the axis of rotation. So we need to determine what this distance h is. So for sphere 1, okay, we have the rod is 10 meters long, so from the outside of the sphere to the axis of rotation, that's 5 meters, and this radius is 2 meters, so h1 is equal to 1/2 the length of the rod plus r1, which is equal to 5 plus 2, which is equal to 7. And for the second mass, same thing. We've got a radius 2 here, so h2 is equal to 1/2 the length of the rod plus r2, which is 5 plus 1, which is equal to 6. So now we can go back to our parallel axis theorem to solve for the sphere. So this becomes 2/3 mr squared plus mh squared. So the I for sphere 1 is equal to 2/3 times 10 times 2 squared plus 10 times 7 squared, which, if you go through the calculations, comes out to be 516.7 kilogram meter squared. And the I of sphere 2 is equal to 2/3 its mass, which is 4, times its radius squared, which is 1, plus the mass times 6 squared. And if you go through that calculation, that comes out to be 146.7 kilogram meter squared. So to get, you add all the moments of inertia to get the I total. So we add the I of the rod plus the I of sphere 1 plus the I of sphere 2. So that becomes 50 plus 516.7 plus 146.7. So I total, the moment of inertia of that whole system, is equal to 713.4 kilogram meter squared. And that's how you use the parallel axis theorem.